So we were doing yesterday electron configurations, how to write electron configuration. We discussed 4 quantum numbers. And today we are going to continue with these electron configuration. Quantum number I'm not going to repeat. So you can practice. And I discussed with you the three basic rules on which the electron configuration is based. One is Aufbau principle. Second, Pauli's exclusion. Third, Hund's rule. Do you remember that? So what was the Aufbau principle? That electrons are filled in increasing order of energy. Increasing order of energy. So no one remember this? Bhavya, do you remember that? First. Bhavya, are you there? So electrons are filled in increasing order of energy. That's for how we decided the electron will go in 1s first, then 2s, then 2p, like this. Second was Pauli's exclusion principle. Any one of you? Pauli's exclusion principle. What was it? Arnav? What was it? Yes, Shriya H. No, yes. Okay, please don't say yes. Answer my question. Pauli's exclusion principle, that inside an orbital, you can have only 2 electrons with different spins. That was the principle. Yes, Bhavya. Very good. And then third was Pauli's exclusion principle, that in an orbital we can have only 2 electrons. Bhavya is giving us very nice definition. But Bhavya, this you have made on your own? Oh, okay. Third is your Hund's rule. Answer my question. Please don't uh, put the complete answer here. Hund's rule. Do you remember the degenerate orbitals? What are degenerate orbitals? Yes, children? Shriya H? Degenerate orbitals. Yesterday I said that, okay, focus on degenerate orbitals. Orbitals of the same energy. Very good, Shriya R. Orbitals of same energy. So in the p subshell, how many degenerate orbitals are there? How many degenerate orbitals are there in p subshell? In d subshell? In f subshell? If you remember, S has only one orbital, so there is no degenerate orbitals in. No, answer my question, Bhavya. My questions are here. In p subshell, how many degenerate orbitals? Yes, Arnav, very good. 3. In d subshell, Shriya H, perfect. In f subshell, 7. Now, now we can discuss Hund's rule. When the electrons will be filled, they will be filled singly first in degenerate orbitals. So first they are going to get filled singly and then pairing starts. Yes, and then pairing starts. Okay. Now I'm going to teach you here another concept. We call it as half filled. Half filled and completely filled subshells. Completely filled subshells. So please write on this. Half filled and completely filled subshells are extra stable configurations. Extra stable electron configurations. EC means electron configuration. So half filled you can put in front of half filled exactly half filled. Exactly half filled or completely filled subshells. What are subshells? There are four subshells. And what are those? Four subshells. In the periodic table, there are four subshells. Mm-hmm. Yes, Shreya R. Very good. SPDF. S, P, D, F. So, Arnav, that's how you can remember also. I want your 100% attention here, okay? These are the four subshells. Keep memorizing, keep practicing, and don't lose your attention. That's the reason I asked you to answer every question. So, S subshell has only one orbital. This is S. S. If I say S2, then it is completely filled. There is no concept of half filled in S, only completely filled. This is extra stable configuration, S. What about P? Can you give me exactly half filled P? P3? Exactly half filled. Then you have 3 electrons with parallel spins. Exactly half filled D. 5 electrons with parallel spins. Exactly half filled F. 7 electrons with parallel spins. You remember Hund's rule? These are extra stable. Exactly half filled P, exactly half filled D, exactly half filled F. Electron configurations are extra stable. Arnav, is it okay? Okay, you can ask the question which I think I answered yesterday also, because these electrons, they can interchange their spaces because they have the same spins. So this can come here, this can go here. This can come here, this can go here. They can interchange their spaces. So they are more free to move around. Like for example, if I keep Arnav in a very small room for 1 hour, he will become very restless. But if I make the room slightly bigger, he will say, okay, thank you. Then after 1 hour, he will again become restless. If you make it more and more bigger, more and more space available to move around, more is the stability. We are going to learn a factor, entropy, in unit 9. Entropy means the randomness, the measure of randomness, the degree of freedom. That's entropy. More is the entropy, more is the stability. Same here. When the electrons can move more into each other compartment because of the same spins, of course, they are not going to be present together. If one moves here, the other goes out. So they are interchanging. This results in stabilization. Extra stable electron configuration means electron has more energy or less energy. Yes. Electrons have more energy or less energy in extra stable? Electrons have more stable means? Bhavya, you are my very old student. More stable. Something is more stable. Shriyaj, I was giving you this mantra. More attraction means? More stable. More stable means less energy. So how come you are forgetting this every time? So please memorize it, make a box, repeat it, speak loudly on your end. You should not forget this. Arnav, you are with me? You didn't answer it? No, 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 yes. What is the answer? Less energy. This electron configuration, the electrons in this electron configuration. So ask your question, why you were not sure? Are you sure now after checking this mantra, chemistry mantra? Arnav, is it clear now? But writing and have you understood this? Because I have given it 2, 3 times. This mantra I have given 2, 3 times. You have understood this? You have to take this part. More stable means less energy. Anything more stable means less energy. So I'm saying this configuration is extra stable. So it means it has less energy. Gorika, is it clear? Gorika. Okay. So children, I've seen those who are answering here and doing the quizzes, interacting with me, asking questions. They are definitely 5. You want 5 in your AP chemistry? Then please use every minute of the class. Keep interacting with me. I'm asking so many questions. Answer them. If you're wrong, I'll correct you. But don't take an excuse of typing or something. I'm not asking you to write down the complete sentences. Only yes, no, this is the answer, less, more, like this. I don't think it's going to take much time. You children are very smart in typing. With your friends, when you chat, you're very fast there. So we are good with this. Extra stable configurations. So exactly half filled and completely filled subshells are extra stable. So S2 extra stable, P3 extra stable, D5 extra stable, F7 extra stable, P6 extra stable, D10 extra stable, F14 extra stable. So please write down this in a box. These are the configurations which are very stable, have low energy, and it will be difficult to disturb them. You need a large amount of energy to disturb them. Disturb means to break them, to add or remove electron in them. My language is clear? Okay. Now, after learning these 3 rules and the exactly half filled and completely filled subshell are extra stable, I'm coming back on the electron configurations and we are going to decide the general configuration of every family. So, and we are going to work first with the main periodic table. Okay. Can you write down the electron configuration of lithium in noble gas notation, children? Rubidium in noble gas notation? Yes, lithium. Noble gas notation means in terms of helium. Rubidium in terms of krypton. Yes, Bhavya. Helium. Shreya H is again first, Shreya R is second, always. They are the first one to answer. Shreya H and Shreya R. 2s1. What about rubidium? Arnav, good. Krypton. Bhavya, good. 5s1. You check any configuration like potassium, cesium, check any one of them. Don't you think that their outermost shell has only one electron in all of them? This is 1s1, this is 2s1, this is 3s1, 4s1, 5s1, 6s1. So what's the configuration of the outermost shell? Outermost shell, this one, s1. So the general configuration of group 1 is ns1. Agreed? Bhavya, is it okay? What is n? N is the period number, principal quantum number. 1s1, this is 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. Shreya R, am I clear? So n means n can be any period. Now the way we decided the general configuration of group 1, can you decide the general configuration of group 2? Pick up 2, 3 examples, write the noble gas notation, and then think about it. Okay, Shreya H is answering it. Is she right, children? Take your time and check whether she is right or wrong. Arnav, just see the configuration of 2, 3. Is she right or wrong? Arnav, what is your answer? Correct. Okay, yes, N is 2. N is 2. These are the valence electrons. Group 1, you remember yesterday I told you the valence electrons are equal to the group number of the main periodic table. Do you remember the main periodic table, children? This is the main periodic table, right? Okay, moving on. Give me the general configuration of B, boron family. This is boron family. The first group is also called as alkali metals. Alkali metals. They are metals because they lose electrons. Second group is called as alkaline earth metals. Alkaline earth metals. Now we are getting familiar with the names of the families. This is called as boron family. Pick up any 3 elements. Just pick up boron and aluminum. You can pick up any 3 and then see the outermost valence shell. Only the valence shell, children. The valence shell is the one with the highest principal quantum number. Mhm. Oh, complete valence shell. All of you are wrong. Shreya H is wrong. Bhavya, you are wrong. Arnav is wrong. Okay, let's pick up indium. Is krypton 5s2, 4d10, 5p1. And Shreya R is right. Valence shell is this, the highest principal quantum number. So what's the general configuration of boron family? Ns2, include this, Np1. The outermost shell, Arnav, Bhavya, Shreya, clear? Now let's see the C part, Gorika. Gorika, let's see carbon family. Mhm. Give the general configuration of the carbon family. Pick up any two elements, check their outermost shell, and just make it a general configuration. Yes, NS2, NP2. That's the general configuration. Yes, yes. Gorika, good. Arnav and Bhavya, both of you are late. Now let's see the next one. Nitrogen family. Give the general configuration. Oh, you did the first? Let me check. Yes, Bhavya, that's excellent. You're making me happy. Now, nitrogen family. Perfect, 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 and perfect. Yes, NS2, NP3. So, this complete family has how many valence electrons? Complete family? You have to become master of this valence electrons because unit 2 is completely based on it. Unit 2, unit 3, Lewis dot structures, chemical bonding. It's based on valence electrons. So, you have to master it. Okay, valence electrons for group this group. Can you define valence electrons, Arnav? Valence electrons, Arnav. What's the definition? Electrons in the outermost shell. So how many are there in the outermost shell? Yes. How many are there? Yeah, count the electrons, Bhavya. She is trying to show me the outermost shell. Count it. Can you count the electrons, Bhavya? Yes, five. Yes. Arnav, five. You have to take all the electrons of the outermost shell. These are five. This is three. This is two. Five. This has five valence electrons, all of them. How many in carbon family? How many valence electrons in carbon family? Yes, please. Yes, four. In boron family? Okay, let's work out the general configuration of oxygen family. We are working with oxygen family, children. Yes, Bhavya, that's perfect. Perfect answer, Bhavya. NH2, NP4. How many valence electrons? Six. So Bhavya is going to be first now. Arnav, good. Now, halogen family. General configuration of halogen family. NH2, NP5. Very good. So the halogen family is NH2, NP5, and oxygen family is NH2, NP4. We need to know these configurations. How many valence electrons in halogen family? Okay, now let's come to the last family, which is very popular family, very stable, least reactive, very stable, least reactive. Yes, why this family is so stable and least reactive? Least reactive means least energy. They don't have energy to react. Why this is so stable? Yeah, this is the completely filled shell with 8. The shell, the outermost shell is fully filled with 8. Remember, I gave you a rule exactly half filled and fully filled subshells. I said subshells. I didn't say shell over there. Shell is only of noble gases. Others are either they are exactly half filled or they are fully filled subshells. But only noble gases have completely filled shell with 8. And that makes them totally inert, non-reactive, right? Give me 1 second, children. Give me 1 second. Okay, sorry, I'm back. Okay, so you have understood the meaning of the noble gases, inert gases. They don't have any tendency to gain or lose electrons because they are extra stable, right? I'm audible, right? Okay, fine. So now you're going to pick up the configurations which are extra stable because they are exactly half filled or fully filled subshells. Can you tell me which families? You can see all the general configurations. This is 2, this is 3, 2, 2, 1. There are two families which are extra stable electron configuration. They are not as stable as noble gases, but they are more stable as compared to other elements. Which two families? Yes, Bhavya. Which two families have exactly fully filled or half filled subshells? Mhm. Leave this NS1 because as subshell we are not going to consider for exactly half filled. What about this one, NS2? Alkaline earth metals, fully filled subshell. So, second family. What's the name of the second family? Alkaline earth metals. They have extra stable electron configuration as compared to other families, as compared to alkali metals and the boron family. This is more stable because it's fully filled. Can you check who is next? Is this NP1 exactly half filled? No. NP2? No. What about this nitrogen family? The fifth group or 15th group or nitrogen family. What do you think? Extra stable? Yes, because it is exactly half filled. Exactly half filled, extra stable. So why are we learning this extra stable configurations? Because they are more stable, so you will find it difficult to remove or add electron in them. Very soon we are going to do periodic trends and you will see exceptional behavior by these families because they are more stable. Noble gases are extra, they are stable, totally stable, not reactive. But these are also less reactive. They are not like noble gases, but less reactive as compared to the other families. We are clear about it? Any question here, children? Okay, good, Arnav. So, can you tell me, Arnav, what are the two families from the main periodic table with extra stable configurations? Two families. All of you, please type the name of two families with extra stable, fully filled subshells. And Bhavya is the first one. What's the name of the fifth family? Name of the fifth family. Shreya is just giving me the configuration. Perfect, Shreya. But what is the name of the fifth family? Are you talking about this family, Bhavya? Yes, nitrogen family. Yes. And what is the name of the second family? This one. If you have, you must take out at least 10 printouts of the periodic table, because next two classes, maybe the next weekend also, I'm going to spend time with the periodic table. So you can put on the periodic table on the information. Periodic table number one, general configuration of all families. Then in the second, you can highlight extra stable configurations like this. So try to write information on the periodic tables. So you must have to minimum 10 printouts with you. Okay, moving on. And due to this stability of exactly half filled and fully filled, there are some exceptional configurations in the D block also. We are going to discuss only D block. Can you give me the electron configuration of chromium? All of you, please. Chromium. In noble gas notation. So there is no need of writing 1s2, 2s2. Start from argon. You are here. And do you remember this is? Okay. Shreya R, Shreya H. Very good. So it is 4s2, 3d, 4. Arnav, good. Bhavya, good. Okay, Gorika, your answer is not there. Now, let's see that actually this configuration is not there. In place of this configuration, one electron jumps from here and goes over here. It's like this. 4s1, 3d, 5. This is the configuration of chromium. This one, not this one. What is the reason? Electron jumps from 4s to 3d. Why? To get extra stable, exactly half filled d orbitals. In this manner, you are getting extra stable d orbitals because there are 5 of such orbitals. So stability is more because electron is free to move in any one of them. More freedom, more entropy, more randomness. So in the D subshell, and same thing will happen in F, but we are not learning about F. We'll be limited ourselves to the D only. In the D subshell, one electron jumps from 4s to 3d to make this 4 as 5. Agreed? Are you okay with this? Now, based on the same understanding, can you give me the electron configuration of copper metal? Now use this understanding. Extra stable configurations which are exactly half filled and fully filled. After using that, give me the correct configuration of copper metal in terms of argon. My question is clear, Shreya? Shreya and Shreya, we are writing the configuration of copper metal in terms of more stable configuration. Mhm. And that's the right answer. Yes, no, Shreya, you didn't jump the electron. You're writing extra electrons. Shriyar is right. Bhavya is right. Perfect, Bhavya. Arnav, waiting. Gorika, you have understood the question? You have understood. Okay, good. Good. These are the two exceptional configurations which are not going to follow the Aufbau principle. Electron will jump from 4s to 3d to make it more stable configuration. Okay, are we clear about it? Aufbau principle, you remember? Filling of the orbitals in the increasing order of energy. 4s has lesser energy than 3d. So electron should go in 4s, but rather than in 4s, it is jumping to 3d to get extra stable configuration. It's the game of energy only. Okay. So now you're going to give me the general configuration of this family. Include this. So I give you one of it. This is D1. So I'm going to say ns2 n minus 1 d1. Can I say that for this canadium family? Because if this is 4s, this is 3. If this is 5, this is 4. So n minus 1. ns2 n minus 1 d1. What about this one? Titanium. Can we work with titanium? Family, complete family, general configuration. ns2 n minus 1 d2. d2. d1, d2. Are you getting this, children? Please confirm. Is it clear? Yes or no? Because then I'll start asking questions. Okay. Bhavya is saying yes. So Bhavya, after understanding the exceptional behavior, can you give me the general configuration of chromium family, the one which is more stable, and of the copper family? Yes, please, all of you. Get the general configuration of chromium family, which is extra stable because of the exactly half filled configuration. One electron jumps from S to D. Waiting for the answer. And Shreya R is right. So the answer is NS1 N minus 1 D5. Yes, very good, Bhavya. Shreya H, very good. Shreya H, right. Yeah. Can you do this one? And that's the perfect answer. So this family, copper family, will be NS1 N minus 1 D10. Now please give me the general configuration of the next family also. Zinc family. General configuration. And Shreya R is right. Arnav, you're getting all these things? Arnav, good. Bhavya, good. Okay. So that's about the general configurations and the stability of electron configuration, which are going to play a very important role in periodic trends. So this is very important and will be tested for it. Now let's write down the electron configuration of the ions. So before we go for the electron configuration of the ions, you already know that ions are either they are positively charged or they are negatively charged, right? So the positively charged are called as cations And negatively charged are called as anions. Cations are formed by losing electrons, loss of electrons. That's why they become positive. They have more protons, less electrons. So loss of electrons. Anions are formed by gain of electrons, right? Gain of electrons. We are okay with this? Okay, now we have to see that why these elements they want to lose or gain electrons. So if you remember, noble gases are the most stable configurations with the minimum energy of the configuration, very stable configuration, completely filled octet. They are unreactive because they are very stable. So every element of the periodic table tends to become stable by acquiring these configuration. Elements of the periodic table, they want to be like noble gases in their electron configurations. So what these elements are going to do? I'm talking about the main periodic table. They will either lose or gain electrons. Losing, gaining electrons is again energy process, means energy needed to remove an electron. So if energy needed should be compatible, you cannot gain 5 electrons, 6 electrons. Maximum you can gain 1 electron, 1, 2, 3. Means elements can have a negative charge starting from -1, -2, -3, not more than that. The charge cannot be not more than -3 elements in the when they are gaining electrons. Similarly, the positive charge will also go from 1, +1, +2, +3, not more than that. Because it's difficult. It's difficult to gain extra negative, extra positive. Energy wise, not compatible. Energy will go very high. Nature doesn't want high energy. Nature wants low energy. So up to this, okay. Not more than that. Can you tell me the first family would like to gain or lose? And how many? They want to go to the nearest noble gas configuration, like lithium. Its configuration is helium 2s1. So what lithium would like to do? It would like to lose electron or gain electron. How many, Shreya, are? How many? Yes. What about potassium? Would like to gain or lose? This, you can also answer, Gorika. I just want to see whether you have understood my question. What about cesium, Gorika? Would like to lose or gain? How many is going to lose? Gorika, you're there? So the first family is going to lose 1 electron. Gorika, I didn't get answer from you. Are you there? Okay. Now only Gorika will answer. Rest, all of you, please think. Strontium. I just want to be sure whether you have understood or not. Strontium would like to lose or gain, Gorika? And how many? Remember, this is NS1 and this is NS2. What strontium would like to do? Very good. It's going to lose 2 electrons. Good, Gorika. Very good. So all of them would like to lose 2 electrons. What about aluminum? Yes, all of you please answer. Aluminum would like to lose or gain? Lose 3. So these are the one which are losing electrons. They are metals. Metals, they always lose electrons. This you know very well, right? If you don't know, please write on. They lose electrons. They acquire a positive charge on them. What do you think? What silicon can do? I said the limit is maximum plus 3. After that, it will become very difficult. So what silicon can do to go to the nearest noble gas configuration? You see it has 14 electrons. The nearest noble gas has 18 and 10. No, 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 dear Bhavya. You cannot gain 4 electrons. You cannot lose 4 electrons. So it will prefer to sharing. It's very difficult to lose such a large amount of electrons or gain such a large amount of electrons. That's why carbon is very unique. Carbon is most of the time sharing electrons. What about P? What P can do? Non-metals, they all can share also, but they can lose and gain also. What P can do? Is it can gain or lose? P, phosphorus? Yes, it can gain 3 electrons. So non-metals, either they share electrons, non-metal can share electrons with non-metals, either they share electrons or gain. Share electrons or they gain electrons. That's a very important line, and you have to understand and you have to use it. So we are understanding that how these ions are formed by losing or gaining. Now, when you are writing the electron configuration of an ion, you are going to add or remove electrons from the outermost shell only. Outermost shell. Ready to answer? So I will give you ions and you are going to give me the configuration of that ion. Remove electrons or add electrons in the outermost valence shell. Don't touch inner shells. Cl minus. Give the configuration starting with neon. Yes, please. So first of all, 1 minus is it means gaining 1 electron. So you write the normal configuration of chlorine atom, add 1 extra electron in the outermost shell. Yes, Shreya is right. It's neon 3s2 3p6. Very good. Yes, Shreya H. Very good. So remember, electrons are added and removed in the outermost shell. Can you do this B3 plus? Do not touch inner shells. Okay, this is for chlorine. Bhavya, where is your answer? B3 plus. Bhavya, you are there? You have not even given the answer of this one. Where is your answer, Bhavya, for this? You have given the answer? No. B3 plus. Now work with B3 plus. B3 plus means 3 electrons are removed. So, what's the configuration? So first you write down the normal configuration 2s2, 2p1. These are the outermost shell 3 electrons. Remove it. Just remove it. So what's the configuration of B3 plus? Just helium. Just helium, right? B3 plus. What happened, children? You're unable to write B3 plus? So what do you do? First you write on the configuration of boron. Then from the outermost shell, remove 3 electrons. Remove, because this is positively charged. Ready for another? Mg2 plus. So first give me the configuration of, first write the configuration of Mg. Then from the outermost shell, remove 2 electrons. And then what is left? That is the configuration. Waiting for the answer. Bhavya, Mg2 plus. Yes, Shreya, you're right. Yes, Bhavya, you're right. It's neon. It's stable. But why I'm not changing the symbol? Anyone? I'm not changing the symbol of this Mg2 plus as neon. Who will answer this? The symbol is still Mg because the identity of the element is due to protons. It's still Mg because it still has 12 protons inside the nucleus. Neon has only 10. It has 10 protons. Magnesium has 12 protons. That's why the symbol is not changing. It has not become neon completely. You cannot say, okay, now let me replace Mg by Ne. No, no. It is Mg2 plus now. Because protons are the identity of the element. So please write on this also. Protons are the identity of the element. Identity of the element changes only by changing the number of protons, which can happen only in nuclear reactions, not in chemical reactions. Okay, I got only 3 answers. I hope, Arnav, you're okay. Arnav, you're not answering. You have stopped answering. You're tired. Arnav, why you're not answering? Why I have to call your name? Yes, Gorika. Good. Now I'm giving you another one. O2 minus. So first, you write on the normal configuration of oxygen, which is here. And then add 2 electrons in the outermost shell. Shreya R is ready with the answer. All of you, please. Shreya H is also ready. Arnav is ready. Very good, Bhavya. So it's completely filled. It's like argon. Oh no, it's like neon, right? Neon. But I'm not changing the symbol. Why I'm not changing? Bhavya, I request you to come back as fast as possible. Because I'm teaching a new concept now, children, which is very important for any competitive examination. How to write down the configuration of the ions in this D block. Let's work out the configuration of Fe. So this I'm going to give you example and then you start doing it. Is argon 4s2 3d 6. That's the configuration, right? Of the Fe. Which one is the outermost shell, children? The valence shell of Fe. What is the valence shell? Valence shell is the one with the highest principal quantum number. So please answer this. What is the valence shell? What is the valence shell here? There are two shells. One is 4, other one is 3. Which one is the valence shell? Valence shell is the outermost shell with the highest principal quantum number. Yes, Shriya H. Very good. Thanks for answering. What about rest of you? Not interested in answering or you're not understanding? Are you understanding this? Shriya R, is it clear? Okay. Now, when I will ask you to write down the configuration of Fe2 plus, if I ask you to write down this Fe2 plus, I will remove electrons from the valence shell. From this, not from 3D first, from here. And the configuration becomes AR3D6. And if I say write down the configuration of Fe3 plus, so it means this is the configuration of Fe. This is the valence shell. So you remove 2 from here, 1 from here. So what is left? What is left? Fe3 plus, 3 electrons are removed. Yes, 3d5. Yes. Very good, Bhavya. And if I say out of Fe2 plus and Fe3 plus, which configuration is more stable? Use that concept of fully filled, exactly half filled. Which configuration is more stable? Out of these two, which configuration is more stable, children? Fe3 plus. Perfect. Again, Bhavya. Very good. This is right. This is more stable. And these are also called as oxidation numbers. So in the nature, which oxidation number is more stable? This one. This is more stable. Not the higher one. It's not always high. Yeah, you want to say, so say 3 plus is more stable because it's 3d5. In this case, yes. 3d5. Perfect, Bhavya. You have understood from where to remove the electrons? Gorika, can we do one question now? Give me the configuration of Mn2 plus. So what you do? First you write the configuration of manganese. Then you select your valence shell, the outermost shell with the highest principal quantum number, and then remove electrons from there. How many? Only 2. So let's do it. And you are wrong. Which one is the valence shell? Shreya, you were not answering earlier, so I was just wondering whether you have heard what I said. First, you check your valence shell and remove electrons from there first. Right again. Manganese is argon 4s2 3d5. The valence shell is, all of you, please type the valence shell here. What is the valence shell? What is the valence shell? Arnav, what is the valence shell? No, here, in this case. I know valence shell is the outermost. But in this case, which one is the valence shell here? You're looking at that, what I'm asking. I'm just making boxes, placing lines. No, you're wrong, Arnav. Your Bhavya, Arnab, both of you are wrong. Gorika, you are wrong. Only Shreya H and Shreya R are right. Please understand, work with me. Listen every word very carefully. It's not a very difficult thing which I'm telling you. Valence shell, I have given you this definition in the last class also. Shell with highest principal quantum number. Arnav, are you processing this? Highest principal quantum number. Be smart, okay? Quantum number. Please look where my pen is writing, where I'm highlighting, where I'm placing lines. That is my question. Now, out of this 4s2 and 3d5, 4 and 3 are the principal quantum numbers. Now decide which one is the valence shell. Arnav, now you type which one is the valence shell. Is it 4s or 3d? So you will remove electrons from there first. How many you want to remove? 2. So what's the configuration? Give me the configuration now. Gorika, understood? Yes, that's the configuration. Good, great. Okay, now without error, you're going to answer this question. So this is argon 3d5. Can you give me the configuration of zinc 2 plus? All of you. I won't answer from everyone. Okay, write the noble gas notation also in front of it, Arnav. Write the way Bhavi has written. Yes. Gorika, same answer? So this is your argon 3d10. And it is very stable. It's fully filled. See, fully filled. So in fact, zinc has only one oxidation number, 2 plus. Like other elements, they can show you variable oxidation number, 3 plus, 2 plus. Like Fe can show you 2, 2 plus and 3 plus. But zinc is going to show you only one, zinc 2 plus. Cadmium only one, cadmium 2 plus. That's it. Because after that, they get very stable configuration. This one. Ready for another question? One last question, and don't do error here, children. Give me the configuration of chromium 2 plus and chromium 3 plus. So write the configuration, that extra stable D5, then check the outermost shell and remove electrons. In one case, you have to remove 2. In another case, you have to remove 3. Very simple concept. Remove electrons from the valence shell, the one with the highest principal quantum number first. Okay, that's the perfect answer. Argon 3d4. Very good, both of you. Because chromium is argon 4s1 3d5. Now you want to remove 2. One will go from here, one will go from here. Yes, D small, Arnav. Can we do this chromium 3 plus Arnav now? Now you have seen the configuration. You want to remove first from here. So it is, yes, very good. Argon 3d3. Now I'm giving you a slightly tricky question. Again, trick is the same. Identify your valence shell. And you will remove electrons only from valence shell. Don't touch inner shells. That's the same trick we are going to play. Give me the configuration of tin 2 plus and tin 4 plus. Tin is here, children. So first, you write the configuration of tin. Then you circle your valence shell. Then remove electrons from there. And do the quiz based on it on the website. And Bhavya is right. Perfect, Bhavya. Perfect. She is giving me of the tin 2 plus. So it is krypton 4d10 5s2. Very good. Shreya, Bhavya, Shreya H. And Bhavya is giving me 4 plus also. And what is tin 4 plus? Arnav, tin 4 plus? Bhavya has already answered it. Remove this also. And it will become krypton 4d10. So first you write down the configuration of tin, which is krypton 4s2, oh sorry, 5s2, 4d10, 5p2. Then identify your outermost shell. Now this is of higher energy because it is p. So first you remove this 14.2 plus. Then you remove this 14.4 plus. Arnav, you're understanding this? Okay, good. So that's the writing of the electron configuration of the ions. Now we are learning this isoelectronic species, very important term. Iso means same. Electronic means electronic configuration, same number of electrons. So these are the ions with exactly same number of electrons. Can we see how? Na plus. How many electrons are there? Check the periodic table. How many electrons are there in sodium metal? And if I put a plus charge, then how many? Please answer. Na plus has how many electrons? Check the atomic number of sodium. What's the atomic number of sodium? Mhm. 11. So it has 11 electrons, right? Electrons, sodium metal. But if I say Na plus, then how many? One electron is taken away, 10. Yes. So Na plus has how many electrons? 10. F minus, neon, O2 minus, N3 minus, Mg2 plus. So what's the configuration? Give me the configuration of these ions. Configuration will be same because number of electrons are same. Can you give me the configuration of these ions? Electron configuration. Yes, please. Electron configuration for 10 electrons. Start with 1s. Yes, it's neon. It's neon. 1s2, 2s2. Give the configuration. That will be 1s2, 2s2, 2p6. So they are isoelectronic. Is the word clear now? So ions can be isoelectronic. They can have same number of electrons after losing, gaining, because they all are targeting the nearest noble gas configuration. So here everybody is targeting neon. Na wants to be like neon, 10 electron. F also wants to be like neon, 10. So they become isoelectronic. If I give you Ca2 plus, can you give me some isoelectronic species with Ca2 plus? Look at the periodic table. Can you check how many electrons Ca2 plus has? Now I want answer from Gorika also. How many electrons are there in Ca2 plus? Gorika, everyone please. Calcium 2 plus has how many electrons? Shreya, are you looking at calcium? Okay, now she is corrected. 2 extra means? Arnav? Means it wants to lose 2. So answer is 18, right? So what's the configuration? Configuration of this ion. Just write the configuration with 18 electrons. Yeah, argon, yes. So can you give me some isoelectronic species? With calcium 2 plus? One is argon, right? Calcium 2 plus and argon are isoelectronic. You can see that. They, there are few more. Yes, K plus. Very good. Who is this? Bhavya, my smart girl. Good. K plus. Yes, Shreya. Very good. Cl minus. Yes, S2 minus. Perfect. Perfect. These are isoelectronic. Don't go for gallium because in between you have D block. So these are isoelectronic. How many shells are there in all of them? How many shells? Number of shells in all of them? Yeah, P3 minus. Who is this? Bhavya. Perfect. They all are isoelectronic. How many shells? Can you check the shells here? 3 shells. Perfect answer. They all are with 3 shells. Perfect, Bhavya. Very good. 3 shells. Arnav, you vanished again? Arnav, 3 shells. You can see 3 shells here. Okay. And how many shells are here in these isoelectronic species? 2 shells. So isoelectronic species will come again in the periodic trends. Now we are on the next topic. We call it as PES, photoelectron spectroscopy. Okay, you have done the electron configuration. You have understood that there are some configurations which are stable because of the fully filled subshells or exactly half filled subshells. Some configurations are totally inert, like noble gases, because they are fully filled shells, right? Now, these electron configurations, we have experimental proof for that. We have experimental proof that this is how electrons are present around the nucleus. And for that, we are going to use photoelectron spectroscopy. Photo means, anyone? Photo means? Light. Photon. Photo means photon, light. What's the formula of the photon? Formula of the photon, children? It's written here on the whiteboard. What's the formula of a photon? A quanta, a photon, Planck's equation, HV. Yes or no? Very good. It's written here. So what we are going to do, we'll take the element, this is potassium, see here, potassium, and we will expose that element to these photons. And then which frequency, this is frequency, right? Which is the form of energy, this is energy, E equal to HV. Planck's equation, children. So when the element is exposed to sunlight, these photons, we are not going to use exactly sunlight because we are going to use a spectrophotometer. We'll introduce the element in it and we'll expose it to the light. Light comes in the form of photons. They fall on the surface of metal. And can you see that if I'm using this much frequency, this much wavelength, this much energy, electrons are not ejected. Electron is not coming out. But if I use this, yes, it's coming out. If I use this, it's coming out. So what is the meaning of this? It means that every electron around the nucleus has a specific amount of energy, quantized. Electrons have quantized energy. You agree with me? And this amount of energy depends on the distance from the nucleus, and it also depends on the stability of configuration. So it depends on two factors. The energy of the electron, two factors. First, distance from the nucleus. From nucleus. Second, stability of electron configuration. Now, this is my explanation. Now, your explanation. I'll start answering here. This is my electron number 1. This is electron number 2. Can you tell me which electron has higher energy here and why? Which electron has higher energy? 1 or 2? And why? Okay, you're not answering it, so answer this. Which electron is more strongly attracted to the nucleus? 1 or 2? So the one which has more attraction will have more energy or less energy, according to that mantra which I told you to write down. Now can you answer this? Which electron has high energy, 2 or 1? Yes, like this. Think like this. I also think like this. Think in a systematic manner. Okay? So always everything can be answered in chemistry if you think like this. Oh, a more attraction, it means less energy. Okay. Now another important way of thinking. If attraction is more, then energy is less. Now when you want electron to jump out, let's say electron is jumping out here to here, out of the atom, and here to here. This is electron 2, this is electron 1. Can you think about that which electron will need more energy to jump out of the atom? In which case I need to supply more energy. For 1 or 2? Shreya is saying 1. Is she right, children? R is also saying 1. Yeah, they are right. Because this is very strongly attracted to the nucleus. and you need a large amount of energy to break this attraction. So more energy is needed to remove this electron which is closer to the nucleus, because it's already with very less energy. So you have to supply more and more energy. You can think like this or you can think like this. More stronger attraction, write on this. Stronger attraction needs high amount of energy to break it. High energy is needed to break the attraction. High energy needed. They have the less energy. Stronger attraction means less energy. But if I want to break the attraction, I need high energy needed. This is different from what I gave you earlier. High energy needed to break it. So don't get confused between these two concepts. Stronger attraction means system has low energy. If system has very strong attraction, then I need more amount of energy to break it apart. Is it okay? Are we clear about this? Based on this, when you introduce an element in the photoelectron spectrometer, then we get a graph, and we should know how to read the graph. In the graph, here is the energy. This is high, this is low. So it means this part is closer to the nucleus. High energy needed. This is the energy needed to remove the electron. So can I say this is closest to the nucleus? Like maybe 1s2, 2s2 like this. And these are the outermost shell away from the nucleus, because less energy is needed to remove electron from there. They are already with high energy. Are you getting it, children? This graph, the coordinates. And here, the height of the graph, the height of the signal will tell you the number of electrons. Like for example, if I have an element, let's say your boron, then its electron configuration is 1s2, 2s2, 2p1. That's the configuration. Now, when I'm going to introduce this in the photoelectron spectrum, I'll get three signals. One signal for this here, like this, because it's closest to the nucleus, hardest to remove, more amount of energy needed. This is my 1s2. Then I'll get second signal, which is the outermost shell, easy to remove. I can put it here. This is my 2s2. Same height. Why? Number of electrons are same, 2, 2. Then I have 2p. 2p has slightly more higher energy than 2s. Slightly, because they are shell number 2. Same shells. So place it closer here and half of the height. This is 2p1. Children, please ask question from here and then we can work out the electron configuration from these PES diagrams. Very simple and they are fun doing questions. Bhavya, any question? Okay. Remember, more protons inside the nucleus, more stronger attraction. More stronger attraction, more difficult to remove the electron. So can you write down, can you tell me how to draw for lithium? You can explain it to me. Lithium configuration is 1s2, 2s1. So this 1s2, shell number 1 will be on more left side, right side. What do you think? It is more on left side or right side? 1s2. Here. It should be here or here. Shriyaj, you're not understanding it? Bhavya? Gorika, you have understood? Gorika, are you there? So can you explain where should I put 1s2? On the left side or right side? When I want to, in photoelectron spectrum, you are removing electrons. So is it difficult to remove electron from 1s or it is difficult to remove electron from 2s? Yes, Gorika. Shriyaj, Shriyar, Arnav, not clear? Which shell is closer to the nucleus? You're wrong. Which shell is closer? So from which shell it is difficult to remove electron because of more attraction? So difficult to remove, more energy needed, put it here. This is 1s2. And 2s1, less attraction, easy to remove, only one electron. So half of the height. This is 2s1. I think you people are finding it difficult to understand. Bhavya, you are not answering. Is it clear to you? Okay, then why you are not answering? Okay, it's okay. It's very simple thing. When you practice questions right now, you will understand everything. Okay, check. This is also called as binding energy, the energy with which the electron is bound to the nucleus. It's the energy needed to break it apart. This is high energy, right? High energy, 100. Can you see how the energy is decreasing? So if somebody asks me, write the electron configuration of this element from this sample, from this PES diagram. What is this? 1s2, 2 electrons. Then what is this? 2s2, 2 electrons, 1, 2. What is this? 1, 2, 3, 4, 5, 6. 2p6. 1s2, 2s2, 2p6. What is this, children? This one. What comes after 2p? It's normal electron configuration, 3s2. What is this? What comes after 3s? 3p1. Can you identify the element? What is this element? This PES diagram is of which element? Aluminum. That's the application part of the PES diagram. Now you can understand that more energy is needed for the shell number 1, then shell number 2, then shell number 3. Okay. Okay. Actually, just don't look at this. Can you tell me which element is this? What is this? In high energy zone. What is this? Shell number 1, 1s2. This one, 2s1. What's the element? What is the element, children? Lithium. Can you identify this element? Okay, what is this one? All of you, please type higher energy, inner shell, closest to the nucleus. So this one is 1s2. This one, 2s2. This one, 2p6. This one, 3s2. This one, 3p6. What is this? Remember, after 3p6, you get 4s first. And it should be completely filled before you go to D. Can you see this one? 4s2, the outermost shell. And what is this? This one? 3D. How much 3D? How many electrons are there in 3D? Check the height. 1. What's the element? Identify the element. Scandium. Yes, Hc. This element is here. So the outermost shell, will appear in the outermost part, because once they get filled, they fall in the right order. Once you're going to fill the 3D orbitals, they come in the right order of the energy. 4s will become higher in energy and 3D will become lesser in energy. The outermost shell will come out after filling. Okay. This is hydrogen. Agreed? Hydrogen element. And it has 1 electron. Can we make helium on the top of it? Helium, hydrogen, and then I want to make helium here only. So these are the questions which can be there. How many protons are there in hydrogen? Nuclear charge in hydrogen? Number of protons? +1. In helium? +2. What's the configuration of hydrogen? 1s1. What's the configuration of helium? 1s2. But which shell? So they have only one shell, right? But which shell is more strongly attracted to the nucleus? The shell of helium or the shell of hydrogen? In which case, there is more nuclear charge, more positive charge in helium, right? So the shell of helium will be more strongly attracted to the nucleus. More strongly attracted means more difficult to remove. So the signal will go to this side or to this side. Where should I draw the signal of helium? To the left side, like this. These are questions. This is based on and the height of the signal will be doubled, right? Height is doubled. This is 1s2. This is for helium. Do you want to see the PES diagram of helium? Hydrogen is around 1.31. This is helium. This is helium. You remember hydrogen was here, 1.31, like this. This is hydrogen, 1s1. This is helium. So what is happening? As the nuclear charge increases, the number of protons inside the nucleus, the shells, they start coming closer to the nucleus. Let's see lithium. Can we make lithium on the top of it? Lithium. Lithium has how many protons? +3. Its electron configuration is 1s2, 2s1. Now this 1s2 of lithium will be like this, right? But is it going to be exactly on the top of this? To the left side or to the right side? This 1s2. This is the 1s2 of helium, which has only 2 protons. Lithium has 3 protons. Yes or no? What do you think? Which 1s2 has more stronger attraction? Of the lithium or of the helium? So the signal will go to the left side or right side? Yes, Gorika? Gorika, please answer. I hope you are understanding everything. Gorika? Gorika, are you there? Okay. You know, if someone who is not answering, I get worried. It's the only thing that's why I start calling the name because I feel that they are not understanding. It will go to the left like this. This is 1s2 of lithium. Now let's see 2s1. This is the next shell. Next shell is easy to remove electron, right? It goes away from the nucleus. Attraction is less. It already has high energy. You supply some amount of energy and it will jump out. So where this 2s1 will go? To the left or right? This 2s1. It will go to the right. This is lithium. Do you want to see lithium? Let's see lithium. Here. Do you remember helium? Helium was here, 2.46, something like this. This was helium, 2 point, I think 46 or 41, something like that. Can you see lithium 1s2 and lithium 2s1? So you are ready for next beryllium? Beryllium. On the top of this, lithium is here. Beryllium is 1s2, 2s2. Lithium is 1s2, 2s1. What's the nuclear charge on lithium? +3. What's the nuclear charge on beryllium? +4. How the signal will go? Mhm. Can you tell me where to draw this 1s2 of the beryllium? To the left or right? To the left. Yes, here, somewhere here. This is 1s2. What about 2s2? Where it should go? To the right of what? This one or this one? This one or this one? This is a 2s1, right? Of lithium. So this 2s2 will be to the right of this 2s1 or to the left of this 2s1? Nuclear charge is still more. It is here. To the left. Who is this? Shriyaj. Perfect thinking. Very good thinking, Shriyaj. I hope you're understanding this. So all these PES diagrams are there in the notes. This is beryllium. Check. The signal is shifting. Both the signals have, both the signals, they are on the right side of the lithium. Lithium is 6.26, 0.52. Beryllium is 11.5, 0.9. So they ask this question, why? Because beryllium has more nuclear charge, so its shells are more strongly attracted by the nucleus. See boron, carbon. See, signals are shifting, right? To the right, because nuclear charge is increasing. This is nitrogen. So can you just check the signal of nitrogen? Can you write it down in your notebook? This is 1s2. This is 2s2. What is this? 2p3. Can I say this is extra stable configuration? Nitrogen, extra stable? We can say that, Shreya? Okay. Look at this energy of 2p3, 1.4. Check oxygen. Oxygen, 1.31. But if I compare nitrogen with oxygen, nitrogen has a nuclear charge of plus 7. Oxygen has a nuclear charge of plus. Yes or no? You have the periodic table. Are you looking into the periodic table? Plus 8. So which one has more stronger attraction? Oxygen. But how come the signal of oxygen, which is 2p4, is to the right side of the signal of nitrogen? See, nitrogen is 1.4 and oxygen is 1.3. Anyone? Nitrogen 1.4, oxygen 1.3. Why is it so? So, you remember the configurations? Is helium 2s2 2p3. This is helium 2s2 2p4. Not because of less electrons, Shreya. If it is because of less electron, then it should be valid everywhere. Then how come it has come only for oxygen and nitrogen? It should be there for the your carbon, boron. All signals were shifting to the right. But here, in a case of oxygen, it is shifted to the left, not to the right, only the last one. Anything else you remember about the configurations? Which one is more stable configuration, nitrogen or oxygen? Which configuration is more stable? Please answer fast so that I can move faster. Gorika, which configuration is more stable? I spent nearly 1 hour on that. Remember, we were writing the general configurations. No, I gave you the rules. Exactly half filled and fully filled subshells are more stable. Then I said in the periodic table, two families, beryllium family and nitrogen families, they have stable configuration. Isn't it exactly half filled p subshell? Arnav, do you remember that? So can you type here, children, again? Which two families, exception is noble gases, so don't write noble gases. Other than noble gases, which two families have stable configuration as compared to rest of the elements? See, Bhavya is writing again. Yes, Bhavya. So isn't it nitrogen configuration more stable? More stable means difficult to remove electrons or easy to remove electron? More stable. Difficult to remove or easy to remove? Mhm. Yes, please. So that is the reason the energy in case of nitrogen is more than that of oxygen. Shreya R, you are not answering. You are there, Shreya R? Are you understanding this? Please ask questions if you have any difficulty. You see the amount of energy needed to remove electron from 2p3 is 1.4. This one. But the amount of energy needed to remove from oxygen, I'm taking you on the oxygen, is 1.31. This one. But protons are more in oxygen. But still, it's easy to remove electron from oxygen than from nitrogen. What is the reason? That's the question they ask. The reason is that nitrogen has extra stable, exactly half-filled p subshell. So it needs more energy to remove electron from P3 than P4. I hope the answer is clear. I'm not getting very good response from all of you. Let's see if we have some question. Which element? Which element is this? It has only one shell. Yes, it is helium. It is 1s2, helium. Which element is this? Yes, it is P, phosphorus. Perfect answer. Phosphorus. Can you draw on the top of this? Yes, Gorika, good. It's phosphorus, 1s2, 2s2. Now I'm making it slightly complicated. You said this is P. Can we draw for sulfur on the top of this? P we know is 1s2, 2s2, 2p6, 3s2, 3p3. And sulfur 1s2, 2s2, 2p6, 4s2, 4p4. Oh, what I did? Something wrong? 3s2, 3p4. Now tell me the number of protons in P. How many protons? Nuclear charge on P. And nuclear charge on S. Now, in which case the shells are more strongly attracted to the nucleus? In which case, shells are more strongly attracted to the nucleus. Why? Why, Shreya? Strongly attracted to the nucleus. Shells have electrons. Shells are more strongly attracted only when the protons are more. Nuclear charge is more. It is S. My answer of my first question is sulfur, not P, because it has more nuclear charge. It has more nuclear charge. More nuclear charge, more attraction. But now my next question, in which case the outermost shell, this one, is more stable? Yes, I think earlier you answered this like this. No, I was not asking for the outermost at that time. Okay, now is it clear? These are two different things. Okay, so in which case it's difficult to remove electron from the outermost p subshell? In P, phosphorus or sulfur? Difficult to remove electron from this particular subshell. Yes, please. Only Shreya R is answering me. It's difficult to remove from P. So rest all will follow the order of nuclear charge, and you will see exception only here, which is this one. This is 3p3 of phosphorus. And this is 1s2, 2s2, 2p6, 3s2. This is for phosphorus. Now let's make on the top of it sulfur. Ready? So when I'm making for the sulfur, these shells, they are more strongly attracted. So they will shift to the right here. I'm making with the other color this color for the sulfur. This is 1s2 of the sulfur. This one, 1s2. This is 2s2 of the sulfur. This is 2p6 of the sulfur. Can you see on the right side? This is 3s2 of the sulfur. But this one is on this side, 3p4. It needs less energy. It needs more energy. Can you see how 3p4 has come on the left side? Oh, sorry, on the right side. Rest all are on the left side. Is it okay, children? You're understanding this? This is sulfur. On the top of phosphorus, I have made sulfur. And only exception is here. All signals of the sulfur are on the left side because attraction is more, energy needed is more, except the last one. P subshell has exactly half filled configuration, which is more stable. So it needs more energy. S is not exactly half filled, so it needs less energy. So here you can observe the exception. Rest all according to the nuclear charge. Shreya R, am I clear? You are good with this? Let's do one last question on PES, then you can try questions on the website. And in the next class, I'll start with the periodic trends. This is aluminum. So you can understand the configuration. Can you, on the top of this, can we draw the configuration of boron? On the top of this, boron. Hmm? What's the configuration of boron? One S2, 2s2, 2p1. What's the nuclear charge of boron? Yes, please. +5. What's the nuclear charge of aluminum? So the signals of the boron will be on the left side or right side? Energy needed will be more or less. So accordingly decide left or right. Signals of the boron will be right side. This will be the 1s2 of the boron. Agreed? And this is the 2s2 of the boron. And this will be 2p1. That's the making of the PES diagram of the boron on the top of aluminum spectrum. You can see how the signals are shifting. So signals are going to the left side, to the right side based on the nuclear charges and based on the stability of configuration. One last question, children. Beryllium. Can we make beryllium on the top of this? So first you write down the configuration. Everything follow a systematic manner. Then you check the nuclear charge. Beryllium is, oh, sorry, not beryllium, magnesium. We are making magnesium. What's the nuclear charge of magnesium, Arnav? Arnav, I hope you're not sleeping. What's the nuclear charge on the magnesium? Look at the periodic table. Get it fast. Group number 2. Yeah, +12. And aluminum +13. Now the signals of the magnesium will be on the left side or right side? Signals of the magnesium will be on the left or right. So you think about of the attraction, in which case attraction is more, in which case attraction is less. Yes, Shreya R. Magnesium signals will be on the left or right? Yes. What about you, Shreya H and Bhavya? Is she right? Arnav? Yeah, it will go to the right side because attraction is less. She's right. Okay. Arnav? Okay, good. What about the last signal of boron and aluminum? Aluminum is 1s2, 2s2, 2p6, 3s1. What about this signal? Which signal will be more to the right or left and why? You said magnesium signals will be on the right, but the last signal is will be different. Which configuration is more stable? Magnesium, this one or this one? Which one is more stable? Remember the rule I gave you? Exactly half filled and fully filled. Yes, Shreya, very good. So if it is stable, so it will be on the left side or right side? Means is it difficult to remove or easy to remove from stable? From stable, it will be difficult to remove. So except this signal, this will be on the left side, this is on the right side. Rest all will shift to the right. This will shift to the right. This will shift to the right, right, but these are left. And the signal will appear like this. I'm making for magnesium with a different color. This is the signal of 1s2 of magnesium. This is 2s2 of magnesium. This is 2p6 of magnesium. Sorry, up to here. 6 electrons. And this is your, oh, aluminum is 3s2, 3p1. Sorry. I did error here, children. Aluminum. You didn't correct me. 3s2, 3p1. So I'm comparing 3p1 with 3s2. This is more stable. This is less stable. So more stable, the 3s2 of the magnesium will be more on this side. This is 3s2 of the magnesium. And there is no 3p for there is no 3p in magnesium. This is 3s2. You've understood this? The shifting of the signals to the left and right. Okay, so please understand that the electron configurations, how to write the electron configuration of the ions, the stability of configuration, exactly half filled and fully filled orbitals are more stable. You'll be tested again in for all these concepts in periodic trends. That will be my next topic. We'll be doing periodic trends. If you come prepared with the electron configuration and understanding of the nuclear charges, attraction, repulsion, then you will do very well with the periodic trends. So I'm going to stop the class now. If you have any questions, you can stay back.